Alright, so let us start a new chapter, the theory of congruence, also known as the arithmetic of remainders, but in fact it's more commonly known as just the theory of congruence. And just like the other chapters of this book, this chapter is also going to start with a little history about the person who is responsible for this idea. And that is none other than the German mathematician Car Friedrich Gauss. I hope I have pronounced it correctly. So he lived in this time period. And this idea came out in 1801 in his monumental work Disquisitiones Arithmeticae. It's in Latin. And this work was submitted at the French Academy 1 year before this year, and it was rejected in a very bad manner. Later, to save their faces, some officials of the Academy made an exhaustive search of their permanent records in 1935 and came to the conclusion that this work was never actually submitted, much less rejected. This, of course, is simply an excuse, the kind of excuse that politicians make when they mess up. But mathematicians, of course, praised Gauss's work. Chronicle remarked that it is really astonishing for a single person to come up with an entire discipline, and that too present it in a well-organized manner, in the manner that he did in this work. And that too at a very young age, because Gauss was only 24 years old when this came out. And speaking of age, at younger ages, this man did many unusual things, which also is expected from such a genius. At the age of 3, according to a well-authenticated story, he corrected an error in his father's payroll calculations. At age 7, when he was 7 years old, his schoolmasters admitted that they had nothing new to teach the boy. In fact, in his very first arithmetic class, Gauss astonished his teacher by almost instantly finding the sum of the first 100 natural numbers, positive integers. He almost instantly calculated the value of this sum. He later confessed that he recognized this pattern. So what he did, he reorganized the sum into small chunks like this. He considered the smallest term and clubbed it with the largest term. And he calculated that sum. And then he decreased the larger number by 1 and increased the smaller number by 1. So 100 got reduced to 99 and 1 became 2. So essentially, he just transferred a 1 from here to this. Because of this, the sum doesn't change, and in fact 2 plus 99 is also 101. And he continued this pattern. If one keeps on going like this, eventually one would arrive at this equation. The sum on the right hand side is unchanged. And if one really continues even beyond this, then one would get actually all these equations again. They would repeat. For example, the very next equation is just this, because if you take a 1 from here and add it to this, you are just going to get 51 plus 50, again equal to 101. So all the equations will be repeated. But there is no need to go any further, because you may notice that all the terms of our original sum have appeared in these equations on their left hand sides exactly once. 1, 2, 3, like this you go to 50, then 51, 52, like that to 100. So now if you add all these equations up, what do you get? The left hand sides are going to give you this. I mean, if you, after proper rearrangement. So that is the left hand side. The right hand side, however, is a number of 101s. How many of them are there? If you use the first terms of these equations on the left hand side to label the equation like this. This is the first equation, so you have 1 here. The second equation, you have 2 here. So this is the 50th equation. So there are 50 number of 101s. And that way, if I use dot, I should put it like this, somewhat bold dot. You see, when you use dot to denote multiplication, make it a little bold and draw it in the middle, not at the bottom. If you put a dot at the bottom, that means decimal point. So this becomes 5050. So pretty quickly you end up with the answer. Now this same technique can be used to calculate the sum of the first n positive integers, where n itself is any positive integer, like this. Say you want to calculate this sum. Where n is a positive integer. Calculate this sum means find another expression for this sum which is somewhat small, okay, and easier to calculate at once. So we are again going to use the same pattern, but this time instead of writing equations like that, what we do, we still choose the smallest term and the largest term and write them in this vertical fashion. And then if we do this, transfer a 1 from one term to the other, in this situation, we are next going to get this. You continue the pattern and you get this. Now this time, unlike stopping somewhere in the middle, we go all the way from 1 to n. So you are transferring a 1 from the bottom numbers to increase the top number. So this is the ultimate increase, and by the time you reach n, the bottom number will be reduced to 1, and the previous step will look like this. And now if you look at the vertical sums, I think you understand what I mean by vertical sums. Sum of these numbers. Each one of them is n plus 1. So this n plus 1 corresponds to those 101s. Okay, now if we add all the things up, then we will actually be getting 2 times our sum, because we are already getting all the numbers from 1 to n and then again once more. So after proper rearrangement and doing everything, on the right side we are going to get a number of n plus 1s. Again, how many of them are there? If you use the top row to label these vertical sums, you realize that there are n number of n plus 1s here. Okay, so that way you get a nice expression for the sum of the first n positive integers. In fact, you already know this. We are introduced to this in school, and we are also taught how to prove it, but Most often this is not the proof that we are taught. We are taught to prove it using induction. Induction has its own advantages and disadvantages. The advantage is that if a statement about positive integers is true, but you don't really understand why it is true, you do not see what is going on inside, which is causing the statement to be true. If you do not get that, induction is a way of bypassing all those complexities and it will give you the proof, provided you are able to do the induction proof. That is the advantage, but that is also the disadvantage, because you do not really know why something is true. You just know that this is true and you have an induction proof. So that's the disadvantage. Anyway, let us continue with our little history of Gauss. Now, these are some little things that he did when he was very young. Next comes some more serious things. And the next thing the author talks about is the problem of constructing geometric figures. Recall that in school geometry, there was a chapter on geometric construction, which also is sometimes titled simply construction. Geometric construction or constructions involves drawing figures using only straight edge and compass and nothing else. And by straight edge, we mean a device like a scale for drawing straight line segments, straight lines, but there are no marks, so that you are unable to really measure lengths of line segments at will. No, you cannot do that. You will be given some unit length and you are able to use your compass to transfer that length anywhere. But that's about it. You can use your compass and you can use that unmarked straight edge, and then you try to draw geometric figures. If you are able to draw a figure like that, then that figure is called constructible. So, it was believed for a long time that the ancient people had already exhausted all the constructible figures, that they figured out which figures are constructible and which ones are not, and this problem was set aside. So it was Gauss who in 1796 showed that the 17-sided regular polygon, which is also known as the 17-gon, is constructible. That means one can draw it in that way, which was the first advance in this area since Euclid's time, because no one else bothered to look at these things. And, well, so this is one thing, and Gauss's doctoral thesis contains a proof of the very important fundamental theorem of algebra. We have already come across one fundamental theorem, but that is the fundamental theorem of arithmetic, which states that any positive integer greater than 1 has an essentially unique prime factorization. This is something else. It states that a polynomial which has complex number coefficients has at least one complex root, which is also a complex number, which if you substitute in place of that indeterminate, then you get 0. And if the polynomial has degree n, using this fact, you are then able to show that it has n complex roots, which are not necessarily distinct, of course. Now, this fact was first stated by Girard in 29 and proved imperfectly in 1746 by D'Alembert and then later by Euler in 1749. So Gauss gave the first rigorous and complete proof. And in fact, in his text that Disquisitionis Arithmeticae, he actually gave 4 different demonstrations of this, 4 different proofs. In spite of all of these mathematical achievements, there are many others. Okay. The most extraordinary achievement of Gauss is in theoretical astronomy. So let's see what that is. On the opening night of the 19th century, on 1st January of 1801, the Italian astronomer Piazzi discovered the first of the so-called minor planets, which nowadays is known as an asteroid, which was later called something Ceres. Now, after this passed the sun, Piazzi observed this. It was observable only through telescope for 41 days, and during that period its orbit swept an angle of only 9 degrees. So after it passed the sun, it just went away, right? Neither Piazzi nor any other astronomer could locate it because they were unable to calculate its orbit. But with the scanty data available, Gauss was able to calculate the orbit of Ceres with amazing accuracy, because the very next year the planet was rediscovered. It was located at almost exactly the same position that Gauss had predicted. And this caused Gauss worldwide fame and led to him becoming the director of the Göttingen Observatory. By the end of 19th century, mathematics had grown so vast that its individual areas themselves became vast subjects, where only experts knew their way. And it is remarked, it's not an exaggerated remark, that Gauss was the last complete mathematician. He knew almost every aspect of the subject of mathematics, and he in fact did something. He was involved with almost every aspect of the subject and did something to some degree in almost every area. And you in fact find Gauss's name in electricity also. Okay, I am not going to remark anything about that. His contemporaries called him Princeps Mathematicorum, the Prince of Mathematics. So what follows next is his story, but this time mathematically. So let us see what it is that we have written. What are congruences? We won't see much tonight. We are just going to see the definition of congruence with a few examples, and we will stop. We will continue in the next number theory video. So the heading is like this: basic properties of congruence. I will, however, before ending the video, make a remark which is not exactly number theoretic. And we have the definition here. So the definition goes like this: let n be a fixed positive integer. fixed doesn't mean exactly one value. Okay, say you fix n equal to 100 and that's just it. No, we do not mean that. We mean that in a given discussion, you fix n first and then you do your discussion with that value of n, that type of fixed. N here has the status of a parameter. Okay, you have parameters in equations, right, where variables change freely or maybe one variable depends on the other. So those things change, but once you fix a value of your parameter, for that discussion the parameter value stays the same. It's that kind of fixed. Two integers A and B are said to be congruent modulo n, or there is another way of saying this. We say that A is congruent to B modulo n. And express it symbolically by writing this. If n divides the difference A minus B. If the integer, positive integer n divides the difference A minus B, then we say that A and B are congruent modulo n, or A is congruent to B modulo n. In fact, that's how you read this symbol. A is congruent to B modulo n, or A is congruent to B mod n, in short. That is, if A minus B is equal to k times n for some integer k. Those of us who are familiar with abstract algebra have already come across this definition. It's a relation. Okay, it's a relation on the set of integers. It's a binary relation which relates two integers. When they are related and there is a modulus of this relation, this number is called modulus of the relation. And it's a special type of relation. We will discuss this thing, but let us first see all the aspects of this definition. So, if n, you see, it makes sense to say that n divides A minus B. Why? Because A minus B, no matter what A and B are, A minus B after all is an integer. So, it may or may not be divisible by n. If it is divisible by n, then we say that A is congruent to B mod n. Now to understand this notion, let us take some actual numbers. This is how the author writes to fix the idea consider n equal to 7. Say the modulus 7 has been chosen. Note that let us note these congruences. 3 is congruent to 24 mod 7. Why? You just apply the definition. 3 minus 24 is minus 21, which is minus 3 times 7. So in place of k you have minus 3 here. In other words, the difference 3 minus 24 is divisible by 7. That is why 3 is congruent to 24 mod 7. Another one, minus 31 is congruent to 11 mod 7. Before we see how this is true, let me also remark that some authors do not use this parenthesis. That way also they write. It's up to us to use or not use parenthesis, but in this book parentheses have been used. So let us see the difference, minus 31 minus 11. So it becomes minus 42. So minus 6 times 7. That is why. Another one, minus 15 is congruent to minus 64 mod 7. How? We see the difference between minus 15 and minus 64, which is 64 minus 15. So this is 49, which is 7 times 7. These examples have been chosen with some care to show that the numbers a and b can be positive, one of them can be negative, both of them can also be negative. In fact, they are any integers. You may have 0 also. And when an integer a is not congruent to some integer b modulo n, then we say that a is incongruent to b mod n. If n does not divide the difference a minus b, then we say that a is incongruent to b modulo n. There is, when you read something, there is no need to, in fact, again and again say modulo, you can say mod, okay. For example, let me write the notation also. In this case, we write a is not congruent to b or incongruent to b mod n. Just like in order to express non-equality or inequality, you strike out the equality symbol, here you strike out this equivalence symbol. For example, 25 is incongruent to 12 mod 7. Do you now realize what this fixing means? We have fixed n equal to 7, then we are changing the integers and see which ones are congruent to which ones, which are not congruent to which one, but that 7 stays the same. And this is because 25 minus 12 is 13 and 13 is not divisible by 7. So 25 is incongruent to 12 mod 7. And this is where we are going to end our discussion for tonight. But before I end the video, let me say something. Once you fix this modulus n, the congruence becomes a binary relation on the set of integers. Say this is the Venn diagram of the set of integers, and for modulus n the congruence is a binary relation. It turns out that this is an equivalence relation. If you do not know what equivalence relations are, you can skip this part. Okay. And this equivalence relation, of course, what equivalence relations do, it also does, it breaks up the entire set of integers into compartments. In one compartment, all the integers are related to one another. Any two of them are congruent to each other modulo n. The same is the case with the other compartments. And no integer from one compartment is congruent to an integer from another compartment. You take elements from different compartments, they are incongruent. You take elements from the same compartment, they are congruent. And these compartments give us systems which behave almost like numbers. There are n compartments if the modulus of the relation is n, and the set of such compartments is your group Zn under a binary operation known as addition modulo n. Okay. In fact, there is another operation, multiplication mod n, so that this becomes a ring. My point is that when you do modulo calculations, actually, in a sense, you are working in this ring or in this group. So this is the algebra perspective of these things, which you can, of course, ignore at this stage because it is elementary number theory, so we need not worry about these abstract algebra things. But if you are interested and you are familiar with these things, every now and then I will draw the parallels. I will show that, oh, we are thinking of congruences in this way. In group language, it is like that, or it is something that we already know about. Okay, we have to still walk a long path to see the parallels between these two ways of looking at the same thing. And that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.